Today we're going to have a look at motors and generators and look at some of the key features and principles that you need to know in this topic. Specifically, we'll be focusing on the motor effect. We'll be looking at AC and DC motors. We'll be looking at why do we need a commutator and what's the difference between a slip ring and a split ring commutator. Then we'll talk about generators, and we'll start by looking at Faraday's law of induction, moving on to Lenz's law, and then seeing how Lenz's law leads to the generation of eddy currents and back EMF. So, looking at the first thing, motor effect. The basic motor effect is the basic principle behind the running of any motor. Stated simply, what the motor effect says is that a current carrying conductor in a magnetic field is going to experience a force. Now, to find out which direction the force is in, you can use either the Fleming's left-hand rule, and that's for FBI, or we can use the right-hand rule. In this set of tutorials, we'll always be using the right-hand rule. Now, a simple example of the motor effect can be this. If I use my right-hand rule, then the thumb points to the current. The fingers point to the direction of the magnetic field, and the force is going to be coming out of the palm. So this is current, this is magnetic field, and this is the force coming out. Now if I take a charged particle and I put it in a magnetic field, it's going to experience a force. So let's have a look at an example. Let's say there's a magnetic field going into the page. And I take a positive charge. Now remember, current is the flow of positive charge, so the current will always be pointing to positive charge. I take a positive charge, and the positive charge is moving to the right. The magnetic field is going into the page, so to determine the force, I will use my right-hand rule, and I get the current is going to the right, the magnetic field is going into the page, so the force is going to be coming up. So the force on this is actually going up. If, however, this was an electron, which is a negative charge, then what we have is the electron is moving to the right, which means that I can't actually use this. The current will actually be going to the left. So my current will be going to the left, my magnetic field will be going in, and the force is actually going to be down. So the force in this case will be going down. Now there's two formulas that you can actually use. If I have a point charge, then I use the formula F equals QVB sine theta. And if I have a wire, so this is for a point charge. If I have a wire, then F equals VIL sine theta. We'll be looking at a few examples of this as we go ahead. Now, how does a motor work? Now, as I said, the basic principle behind the working of any motor is the motor effect. And essentially all I do is this. Let's say I take a wire and I put it in a magnetic field. Right? Using the example that we did previously, let's just say there's a current in the wire and current is going up. Using my right hand, B is going in, current is going up, force is going to be to the left. Now, to make a motor, all I need is I need a magnetic field and I need a wire that's carrying some current through it. So, the simplest way to make a motor is this. I have a north and a south. Let's say I have a piece of wire that is stated like this. So my piece of wire is a rectangular block going in here. So current is going from here back and then coming around, coming forward. So essentially what I have is my current is going into the page over here and my current is coming out of the page from here. Using my right hand rule, magnetic fields are going from north to south. So looking at this side, which is side A, and this side, which is side B. Current is going in. Magnetic field is going to the right. So the force on this side is going to be up. So this side gets pushed up. This side will actually get pushed down. So essentially, this guy will turn. From here, he will turn all the way till there. When he gets to there, the force is going to be pulling it up, and the force is going to be pulling it down. Because they're in opposite directions, there actually will be no force. But this will still keep on moving because of inertia. Eventually what will happen, however, is this guy will turn so that the A comes where B is and the B comes where A is. So now I'm going to have A over here, which was going in, and I'll have B over here, which is coming out. So now what will happen is the force will reverse. On this side the force will now be going down, and on this side the force will now be going up. Why? Because the direction of the currents has changed. Earlier on this side it was going in, now on this side it's coming out. That's why you actually need